Hi, this is Scully Physics, episode on torque and Newton's second law for rotation. When we open a door, it's the most common thing that we apply torque to every day. And this is an overhead view of a door. Generally, the doorknob is located right here, kind of on the edge, so that if you push or pull it, it rotates clockwise, or if you push it, counterclockwise. Okay, so there's a counterclockwise rotation to it. There's a clockwise rotation. You might notice that there's a reason why the doorknob is always on the outside. I've always liked the Hobbit doors. I think there's a doorknob on the middle of Hobbit doors, sometimes portrayed in the middle of the door. The problem with if you push or pull in the middle of the door, it's kind of hard. It's difficult. And go ahead and try it now if you pause this video now. You go to that door and you push on different parts of the door, you'll find that it's a lot easier to push and pull it kind of on the edge of the door rather than in the middle, push or pull, or even really close to that hinge. This is the hinge area over here. So if you try to push or pull really close to that hinge, you find it's really difficult to rotate it. You feel like you have to push it with a lot of force in order to rotate it, and you do. You have to put as much torque on the door to rotate it on the inside as you do on the outside. And that's our topic today. Torque is a rotational analog of force, meaning if you want to accelerate the rotation of a system, you have to apply a torque to it. All right, so there's a couple of pieces that we're going to add on here. When we push on this door, we're going to apply a force to it. So there's a force involved, there's an F, and keep in mind that force is a vector. And there's also a point at which we're pushing on the door. I'm going to call that R, but this R is not just radius, it's got a special name. It's called the torque arm. The torque arm. If you think about your arm, if you hold your arm out like this, you can push on your hand or push on your arm, or it's connected to your elbow. You see your elbow kind of rotates, or if you think about the whole arm itself, it rotates about your shoulder there. There's a rotation to your arm as well. If you're on a spinny chair, you could also try this. If you have someone to help you out, you can hold your arms out when you're sitting on that spinny chair and have them push you, and you'll start to rotate. And try having to have them push on different parts of your arm, your hand or your elbow or in close to your shoulder. You'll find that rotation rates are different. So there's this force, this torque arm. Okay. And our topic today, which I really haven't written out here just yet, is called torque. And I wrote that with a funny T because that's the T that we used, the symbol tau. It's a Greek letter tau. Lowercase letter, it stands for torque. I'll go ahead and write that so it looks a little normal here. So torque is tau. And torque, you're going to get more torque as you push further and further out on the door. So torque isn't just affected by the amount of force you push with, but where on that door, where on that rotating object you push, called the torque arm. And so it can be easily defined and experimentally determined to be force times a torque arm. Now, leaving one little important piece out of this. What if the direction of the force is inward on the door or outward on the door? Would that cause any rotation to the door at all? If you push inward toward the rotation axis or outward from the rotation axis, there's going to be zero rotation, meaning there's zero torque. So this isn't entirely accurate. Instead, because there is an angle involved, we're going to find here in just a minute that it's really R cross. It's a cross product of the torque arm and the force. And if you recall way back, did an episode on the cross product. If you take vector A and cross it with vector B, the magnitude is AB sine theta. Now I just want to help you to see what's going on here. Why is it the sine component that we're being concerned with? We'll start with that board anew and a rotation axis. If this is the force and our torque arm is out, extending from here out to this point, and there's our torque arm. There is an angle between these two of 90 degrees. So it works out really well. If we think about a sine of 90, that would be 1. It would be the greatest amount of torque that you could put on an object if you apply a force perpendicular to its torque arm. Now what if we rotate that force just a bit? Instead of applying a force at that angle, at a perpendicular angle, what if we apply it sort of like this? So we now have a force at an angle. I'm going to dot, dot, dot this. We got a direction of this force here. And our torque arm is still in this direction. There we go. That creates an angle theta between our force and the torque arm. Now let's see where this theta gets involved here. If torque is R cross F and A cross B generically is AB sine theta, then this turns into an RF sine theta. Here's our expression we're working with. Torque equals RF sine theta. This is the magnitude of the torque, how much we're dealing with. We'll talk about the direction in a moment. It's pretty easy. But getting back to this magnitude, if the angle between R and F is 0, in other words, if I pull directly outward from the hinge on this door, then sine of 0 degrees would give us 0 torque. It wouldn't rotate at all. Or what if I pushed inward? What if this angle was 180 degrees? Pushing inward would also give 0 torque. Sine of 180 is 0. So you see how this expression is working out for torque. Now what if, go back to that previous example, what if force is perpendicular to the torque arm? What if it's 90 degrees? Well, sine of 90 gives us 1. That would mean RF, it would be the maximum amount of torque we could give the system if we apply a force at a 90-degree angle to that torque arm. All right, so does it matter whether we do R cross F or F cross R? It kind of does. In terms of the magnitude, no, it doesn't. But in terms of direction, yes, it does. So that transitive property is not in play here. R cross F does not equal F cross R. Because if we try R that goes this way, cross F that goes that way, that means we're starting at R and going up the angle theta. And that gives us a rotation that is counterclockwise. But if we did an F cross R, then we'd be starting with this angle, or this direction, and crossing it towards R this way, and that would give a clockwise rotation. Now if you push upwards on this door here, we should get a counterclockwise direction to it. By pushing up on the door, we shouldn't get the door to swing down. Okay, you see how that doesn't really work there. So while the amount of torque would be the same no matter if you crossed R cross F or F cross R, the direction would be opposite. So be sure you get that R cross F when you're thinking about torque. All right. Now just to give you a visual on this sine theta, why is it sine theta visually? We did talk about how pulling out or pushing in does not rotate the system. So we take apart this force and convert it to its horizontal and its vertical components here. See how that blue, that horizontal component, is the outward direction on the door. It's going to cause no torque at all. So this blue component has no impact on rotating the system. But what about that purple component? All right, do you notice how the angle, my little triangle here, matches the one up here for theta? So this should be kind of an upward direction angle there. Anyhow, those angles match, and it's the opposite side that we're looking for. So if this is the direction of the force F is the hypotenuse, the opposite side here, this this opposite side component of F is the component of the force that is doing the torque, that is torquing the system. So the opposite component times R is really what we're looking for here. And what is the opposite component? It's F sine theta. So therefore the torque would be just F sine theta times R. It's this perpendicular component times the torque arm. And that's what gives us the correct amount of torque on our system. Just want to leave it a little more cleaned up to refer to later on. Okay. So that's solving for torque. I'm going to give you an example of that in just a moment. Now what's the other thing that happens here? Once you apply a torque to this door, what are you trying to do? You're trying to open it. You're trying to rotate it. You're trying to cause an angular acceleration of the door to change its rotational position. Wow. Bet you didn't think that's what's happening when you open a door. But yeah, trying to cause a change to the rotational position of that door. So what is the effect of torque? How does it relate to changing the motion or changing the position of that door? Let's go to an old friend. You might recall that sum of all the forces on a body equals mass times acceleration of that body. Now this is for translational motion. If I want to move a car, I have to apply a net force to accelerate that car. But of course, the amount of acceleration depends on the mass of the car. A fully loaded truck is more difficult to accelerate than an empty truck. Well, here we have torque is analogous to force, and angular acceleration is analogous to translational acceleration. So guess what? Sum of all the torques acting on a system is equal to rotational inertia of that system times its angular acceleration. So this is Newton's second law for rotation. This is F equals ma for rotation. Torque equals I alpha. Okay. So in addition to torque being R cross F, and if we take the magnitude of that, it would be RF sine theta, okay? And of course you got a direction to that, just pull an audible there. What we can do is feed this information into the net torque to figure out what the angular acceleration of a system is. At this time, I'd like to talk about the units of torque. Okay, I've got two forms of it. We got net torque equals I alpha, and we got the generic torque here equals RF sine theta. All right, so what are the units going to be? Well, according to this over here, torque, if let's just drop this sine theta, it could be any number, it could be any angle, but unit-wise, torque equals RF, let's say for a perpendicular force, has units of meters times newtons. All right, so the unit for torque over here is the Newton meter. There it is, the official unit of torque. Well, let's see if that agrees over here. Wow, what is this garbage? Net torque equals. All right, moment of inertia is in units of kilograms meters squared, like that mr squared kind of format. So kilograms meters squared. And angular acceleration is in radians per second squared. Okay, kilograms radians per second squared. Now, whenever you get a radian involved, remember that's just a radian is just a count. It's a number. It's like a number of degrees, number of. So because we have these dimensional units here, radians has no dimension to it. So as I've talked about in a previous episode, unit-wise, we're going to drop that. We're left with kilograms meters squared per second squared. Now, what is a Newton meter? Newton is a mass times acceleration, and then we're multiplying that by another meter, so we get a meter squared per second squared. They both agree. Unit-wise, both of these expressions agree. Now this one, keep in mind, this is the sum of the torque acting on a body relating to its acceleration. And this is just the torque due to a force on the body. Now, there might be multiple forces and therefore multiple torques acting on a body. But here's the official unit of torque, Newton meters, in our international system, or metric system as people call it. Isn't there something else that also has a unit of Newton meters? I did just want to drop in and take a moment to talk about this. You might recall that work, in one of its generic forms, force times displacement, is going to look very similar, actually the same in units as torque. Okay, if we look at these two in their generic forms, this is Newton times a meter, and R is in meters, F is in newtons. They're both the same, Newton meters. This one gets the Newton meter tag. This one, you never write Newton meters for work. You write joules. Or in the English, joules. Okay? You write joules. This is Newton meters. What's the difference? Recall, work is a scalar and torque is a vector. And torque is not energy, work is. What? Do recall, though, just how we came about these. With a displacement, there's a direction to it. With a force, there's also a direction. And you'll notice that the way we come up with torque and work is very similar in nature. We take that x component of force that's in the same direction as the displacement, and that is what work is. When we take F dot displacement, those are vector quantities. We get a scalar value out of it. We get an Fx cosine theta, okay, with no direction. There is no direction to energy. How much gas did you put in your car? 20 gallons north. That doesn't make sense. Okay, there isn't a direction to energy. And there's our angle there. In this kind of rotating system, we also have a force, of course, the torque arm. But the force is at an angle. Angle between the force and the torque arm is theta. And here we have torque equals R cross F. See, I almost did it there. R cross F, and its magnitude is RF sine theta. All right, but in this case, there is a direction. We do have a direction here. This would rotate it counterclockwise. So they both have the units of Newton times meter. Here's a Newton times a meter, but they're very different quantities. Both having an angle. This is the dot product. This is the cross product. No direction with a direction. Same units, but very different quantities. One's an energy, and one is the rotational analog of force. So please note the differences there. Let's get into some examples. This is the seesaw example. Going to the park, we've got an adult and two children, and we're trying to ride this seesaw that's balanced right in the middle. Can the adult do a seesaw with a 20-kilogram kid? Well, that's going to be very difficult to balance. There's a couple ways you could do that. With a 4-meter-long seesaw, you could move the fulcrum to one place. So you've got like the 100-kilogram person over here and the smaller 20-kilogram person over here. Where could we put this fulcrum to balance everything out? That's one way to do it, but I don't think most parks allow you to do it. They usually have this fulcrum, this balancing point right here in the middle. All right. So what if we've got like a couple of kids? We've got let's say there's a 40 kilogram child and let's go with a 50 kilogram child. So the 40 kilogram kid is way out here, and we have a large adult, let's say 80 kilograms out on this side. Right. So what that gives us is a weight out here of 80 times 9.8. Let's say 80 G. And over here we've got a smaller weight of 40 times 9.8. My question is, where should we put this? Where should we put this 50 kilogram child? As a slightly greater weight than the 40 kilogram child, but we want to try to balance the system here. All right, we're trying to balance the system and find R. What is the distance to that 50 kilogram child and from the fulcrum? All right. Whenever we're trying to balance, we go to the law that deals with balancing forces. But in this case, we're balancing torques. Before we get I and alpha truly involved, we're trying to balance the system, which means the angular acceleration should be what? It should be 0. Okay, we don't want any angular acceleration clockwise or counterclockwise. So if alpha is 0, what we're going to have here is the torque from the 40 kilogram child plus the torque from the 50 kilogram child plus the torque from the adult equals I times 0 angular acceleration. Okay, is that possible if we take 3 numbers, add them together to get 0? Yes, it's possible if one of those values, at least one of those values, is negative and at least one is positive. Where's the positive and negative come from here? All the forces are pulling down. So doesn't that mean all of the forces are in the same direction? Translationally, yes, they are. And translationally, there would be a force from this fulcrum pushing upward. But that's not what we're focused on in this scenario. We're looking at forces that cause rotation. So what direction does this adult's weight try to rotate the system? The adult's weight is trying to rotate the system clockwise. You see this point here, this magic fulcrum point? From here to there, this weight is trying to rotate the seesaw clockwise. What about the weight of these two children? That's going to rotate the system, or try to rotate the system, counterclockwise. This one's a counter over here, this one's a counter over here. Those are two different directions. I'm going to call this direction positive. I'm going to call clockwise positive in this scenario. All right, so let's see what happens here. If the 40 kilogram child's torque is out here going counterclockwise, that means there's going to be a negative 40 G. So there's going to be a 9.8 in there. So 40 times 9.8 times the torque arm. Now if this is a, I gave it an audible before, but this is a, we'll call this a 4 meter long seesaw. So from the balancing point to the end there is 2 meters, and out here is another 2 meters. What we don't know is the R value, okay? So the torque arm from the rotation axis out to this point, out to where the 40 kilogram child is, that would be a 2 meter torque arm. And what about the 50 kilogram child? Well, it's also going to be a negative torque. Counterclockwise, I'll show them both here, is going to be negative direction. So there's going to be a 50 G here, but what we don't know is the R value. So I'll leave that as R. And then we've got the torque from the 80 kilogram adult. This is going to be a positive torque, so I'm adding the 80G times how far out? 2 meters out. Okay, that's our expression. There's a couple ways to solve this. One, we can plug in the 9.8, but because we've got a 0 on this side, I could actually divide every one of these terms by 9.8, and those g's cancel. So just for simplicity, I'll do that right now. We have a negative 80 over here. We have a minus 50r and plus 160 right there, and all that equals 0. Now, another way to look at this system is we could say that the torque from the adult is equal to the sum of the torques of the children. See, if we add 80 and 50r to the other side, we just move those over there algebraically, we'd get that the torques going clockwise equal the sum of the torques going counterclockwise. So that's another way to look at the system of balancing. Oh, before I just go ahead and finish this and solve this, there's one piece that I did leave out. Shouldn't we have a sine theta on each of these? And please don't ever forget that. If it is important, do we need those sine thetas? In this case, all of these forces are indeed perpendicular to the torque arms. If we look at the torque arm going out to the adult, there it is, it's perpendicular. Torque arm to the unknown positioned child and torque arm to the 40 kilogram child, they're all perpendicular to the weight forces. So because they're perpendicular, sine of 90 is 1. We could multiply all these by 1, but we're going to get the same result out of it. That's why I like the seesaw. You don't get too many confusing angles involved there. All right, so let's solve this out. 160 minus 80, subtract 80 on both sides there. We get 80 equals 50r, or r equals 8/5, which is 1.6 meters. Now we know where to put the person. Okay, 16/10 is 1.6 meters. And 1.6 meters would be this distance outward from it. So this 50 kilogram child should be kind of right in there-ish. Okay, that's where we should put the kid. One sitting right in front of the other, about 0.4 meters away. There's 1, 2, 3, 4. Yeah, it's, you know, they're sitting together. And they'll balance out nicely with the adult. Okay, that's our seesaw system. Let's go to something a little bit more where we're going to get an angular acceleration now. All right, I'm going to take a solid disk pulley. Here we go. I'll go ahead and give it a mass. Let's make this kind of significant. 5 kilograms. Radius of 0.2 meters. So 5.0. There's 2 sig figs at least here. So mass of 5.0 kilograms and a radius of 0.2 meters. I think I can get that a little clearer for our viewing audience. There we go. And on this side, I'm going to pull 20 newtons. Over here, I have a greater pull of 35 newtons. Let's determine the angular acceleration of this system. All right, angular acceleration given some forces and torques. So tools I'm going to pull out, Newton's second law for rotation. And let's keep in mind that torque equals R cross F. There we go. Okay, so if we are looking for alpha, let's start here. What are the sum of the torques? Well, we've got a 20 Newton torque going clockwise. I'm going to call clockwise positive. That's what I'm starting with. And it is 0.2 meters away from the center. Now over here, we should consider 0.2 times 20 sine theta. The angle between the force and the R at that point that the force is being applied is 90 degrees. It's perpendicular. And the same thing is going to be true for over here. That 35 Newton force is also perpendicular. But it's going in the opposite direction. So I've got a force times the torque arm minus a force times the same torque arm. That's the sum of our torques on the system. This is the axis that's held still. That's going to equal I times alpha. Ooh, what is the I in this case going to be? If we look up the I for a solid disk, it's 1/2 mr squared. Get that 1/2 term in there. So we're going to have a 1/2 times the mass, it's 5.0 kilograms, times the radius squared. And we're looking for the unknown alpha. All right, our net torque on the system is 20 times 0.2, which is 4, minus 35 times 0.2, which is 7. All right, 35 times 2 is 70, times 1/10 is 7. And that equals 1/2 of 5, and times 0.2 squared. That'd be 2/10 times 2/10 is 4 hundredths alpha. Of course, you can do this a lot easier and faster on a calculator. All right, we got a -3 over here, and we're going to multiply these out. We got 20 over 200. All right, that's the same as 1/10. So our alpha would be -3 times 200 over 20. So we get a -30. How do you like that math? Radians per second squared. Kind of a quick spin there, right? Quick angular acceleration. So the negative just means, since I define this as positive in the clockwise direction, negative just means it's in the counterclockwise direction. So we could write that 30 radians per second squared counterclockwise. That'd be the best description of that motion. And that's how you would go from there. All right. As a reminder, what else might happen at this point? It might be like, well, a question might be, what's the angular velocity after accelerating from rest for 4 seconds? Or what's the angular displacement after 4 seconds? And if that's the case, keep in mind we have a constant angular acceleration of 30 radians per second squared. If you're asked what's the omega at 4 seconds, or what's the theta at 4 seconds, the equations of rotational motion are just like the equations of translational motion. Omega final equals omega initial plus alpha t. And we also have theta, like a theta final equals theta initial plus omega t plus 1/2 omega initial t plus 1/2 alpha t squared. Okay, you still have these. Plug them in, give it your initial conditions. They're usually zeros. Plug in your alpha, plug in your time, and you'll have your answers out of that. So don't forget those little pieces. Once you have the alpha, you can figure out the omegas and the thetas from there. So I hope that gets you started with rotation, and I hope this has been helpful overall.